Hope everybody's doing well. Can you guys hear me?
Yes, we can.
Great. Any questions that anybody would like me to address before I dive into where we left off last time? A couple of notes. What I've decided to do for those who are taking the course for credit is I'm going to have one of my postdocs actually write up the homework keys right in the wiki. So for example, can you guys see my screen before everybody see my screen okay?
Yeah, I can see it.
Yeah, look good.
Okay. So for example, the first set of homeworks was at the bottom of this first wiki page. And I'm actually going to have him fill in the detailed key right below these problems. And then I'm going to, for the students that are in the course for credit, what I'd like you to do is go through and self-correct and clear up any misconceptions. And then I'm going to allow you to just self-grade this semester based on effort more than anything. Just, we've been instructed at BYU to try and be somewhat lenient given the fact that things are kind of crazy right now. Any questions on that? Does that seem agreeable to people?
Sounds awesome.
Okay, so Shihui should be filling this in the next, I told him to try and get the first 2 homework sets up on the wiki by the end of the week. So he might do it, I'm not sure if it'll be during the work week or over the weekend. And then you guys can come in and hopefully it will help you learn the material more deeply. Okay, let's go back to where we were. We were looking at taking a little overview of polynomials, and we started with the power basis, and we described that the power basis really, while an important theoretical basis for polynomials, it is not stable from a numerical point of view. And that instability actually can be seen visually if you, for example, look at these guys right here. These are 4th order polynomials. So P is equal to 4, and you can already see the trend. This right here is the 4th order polynomial, the purple guy, and it's becoming more and more difficult to distinguish between x cubed and x to the 4th, in particular on the domain 0 to 1. And so as the polynomial degree goes up, these functions begin to closely approximate one another, and that leads to what we call, you could call it numerical linear dependencies. And either you can get so close that up to machine precision you can't distinguish between one basis function and another, or what we call the condition number. And I keep saying this this term condition number. I'm actually going to write up a whole section on condition numbers next week, give you the scoop on why they're so important. But a condition number essentially at a high level right now, without diving into the details, measures how close to singular a linear operator is, matrix essentially. Okay, so a condition number of 1, we say the matrix is perfectly conditioned. And then as it gets bigger, if it was infinite, that is a singular system. But large condition numbers, large condition numbers indicate that you're approaching what we would call a numerical linear dependency. The reason we care about condition numbers is because the process of solving linear systems with poorly conditioned matrices has some significant drawbacks for both robustness and efficiency, and we'll get into that later.
Is this at all related to what we call a singularity in finite element analysis?
Well, a singularity, you can have a singularity, for example, in a stress field would mean that like a function is blowing up in some unbounded way. So maybe if this was stress, we would say that this is a singularity. It is not necessarily a statement on the associated matrix. It's more a statement of the actual behavior of the solution.
Okay, thanks.
So yeah, so what this means is if I was to say there's a singularity in this problem, like a stress singularity, for example, what that would indicate to you is that from a finite element perspective, from a meshing perspective, in terms of picking your discrete space, you're going to want to try and resolve the singularity, and you're going to need to be aware of it. And there are a number of ways to do that.
Mike?
Yep.
Can you comment on how mesh refinement might affect your conditioning, and what's the most effective way to increase the resolution of your solution space and preserve a well-conditioned system?
Right. Okay. So just at a high level, we'll dive into this more later, but as the mesh size H goes to 0, the condition number goes to infinity. As the polynomial degree goes up, then the condition number goes up. The rate at which the condition number goes up for H refinement versus P refinement is that the condition number goes up much more quickly for increasing to degree. So as you increase the degree, the condition number grows more quickly than just H refinement. And I will look up, I'm going to look up actually you can actually look up the actual rates for these things. And because our method, so in some sense a C0 linear finite element mesh with H refinement is a fairly stable and a fairly nice stable way to discretize an operator from a conditioning point of view. And so as you go up in degree, right, as the degree goes up, which is the methods we're going to be considering, the conditioning gets worse. And so in order to have really robust methods that have using higher order splines, we have to be aware of this issue and deal with it. And so we're going to take a look at that. Really, you want to control this conditioning so that it doesn't just, I mean, it can grow so quickly with degree that it can essentially blow you right off the machine very quickly.
When you talk about the conditioning of P refinement going down, does that have some, I mean, is there an element?
P goes up. So as the degree goes up, the conditioning.
Sorry, that's what I meant. My question was, is there, so we know like a power basis is very clearly unstable. Is there something about the basis functions that we use that cause P to hurt the conditioning?
Yeah, so I mean, that's really what's going on with P. And so what you really want to do is have a way to condition your basis so that you control the condition number. Essentially what you're after with P refinement is that you want to somehow develop a method where P refinement conditioning behaves similar to what you would find with classical H refined meshes. That's the challenge that we're after, we want to solve here.
Are Lagrange bases the optimal basis for conditioning with P refinement?
You know, I don't think that there is a conclusive answer to that question, because conditioning in the discrete setting depends not only on the polynomial degree, but also the points where you sample the domain. And so what you'll find with these bases, like if we move to the Legendre and Chebyshev bases, let's move down here. So these orthogonal bases have much superior conditioning properties in comparison to the power basis, but it also means that to get these optimal conditioning properties, the locations where you sample the polynomials makes a difference, which is why quadrature schemes often are at points for particular bases of polynomials. Like Gauss-Legendre quadrature is the zeros of the Legendre polynomials, because you can show under certain conditions that that essentially is the optimal interpolating polynomial for this space, for this basis. Likewise for Chebyshev, is even probably, I would say, a little more important even than Legendre. And Legendre is kind of a special case of a Chebyshev basis for a particular inner product. But it has these optimal properties, which I describe here, which says that the roots of the Chebyshev polynomials, in some sense, optimize polynomial interpolation. So it minimizes what's called Runge. I don't know if I've pronounced that right. Runge, which is if you take a let's say you want to approximate, you have some function, and you want to approximate that function by sampling it at a certain number of points, and you want the polynomial interpolant of this function to pass through the function at these points. So you want it to actually interpolate the polynomial at those points. The location of the points can give rise to very oscillatory behavior. Like if you pick points that are just uniformly spaced, and then you try and create an interpolating polynomial through those points, it's going to oscillate wildly. That's called Runge's phenomena. It's also related to Gibbs phenomena. You might have heard of Gibbs. Gibbs is oscillation. Gibbs is oscillation with sines and cosines, though. And Runge's phenomena actually is specific to polynomial interpolation. So the Chebyshev polynomials are, in some sense, optimal in the sense that if you pick the sample points to be the locations of the zeros of these polynomials, then what you can show is that the resulting interpolating polynomial minimizes the oscillation. And so it's the closest to the best polynomial approximation. So Chebyshev polynomials are valuable because of this property. And this, of course, these points then give rise to other quadrature schemes. So you can start to see that there's this really close connection to these classical polynomial bases, their zeros, the locations of their zeros, the idea of polynomial interpolation, which is given a polynomial basis, find the best approximation that passes through or interpolates the function at a certain set of predefined points, and the classical quadrature schemes that are all over FEA. Although most people may not know that this is what's going on when they pick a quadrature rule. So, Curtis, to answer your question, it's difficult to answer because not only is it the basis, but it's also where you sample that will determine the resulting conditioning
When you say where you sample, you're referring specifically to quadrature?
Yeah, I mean, that's one way of thinking about sample points. But what I mean is if you want to try and sample a function with a polynomial, and let's say you have, pth order polynomials, then you know that in order to have a rank sufficient operator, you have to have p plus 1 sample points. And the location of those sample points has a dramatic impact on the quality of the interpolating polynomial that you compute. And it's all related. I mean, quadrature is just like, I don't know, it's really nothing more than this idea of finding a best interpolating polynomial through a given set of points.
So Mike, have people made statements about what the minimum error you can expect to ever achieve is, given certain conditions where, there's a limiting case on what a well-conditioned stiffness looks like?
Well, maybe within certain classes of polynomials they have. I have not, and again, this just could be a deficiency of my knowledge, but I have never been able to find an agreement on what's the best polynomial space, best sample points or quadrature points in terms of, especially in terms of conditioning. That, from my perspective, is not, there's no really like definitive guide on that. I mean, you have to really search to even find these kinds of results. So I guess that's going to be our job, is to probably figure that stuff out. But I'm going to go through and find, there are some results, especially for the classical polynomials, where you can kind of show there are some relationships between the basis that you pick and the conditioning of the system. Okay. So I don't know if there's much more I want to say about these orthogonal polynomials, which again, just to reiterate, you construct them from the power basis by picking an inner product and then applying Graham-Schmidt, which is described in the mathematical preliminary section. It's just a way to orthogonalize vectors in a linear space. And so Legendre and Chebyshev are probably the most famous. There are others. There's a whole family of them. Okay, and I'll show you for a little bit later why orthogonal bases are valuable from a finite element point of view, but let me get to that, come back to that point a little bit later. Let's go to the Lagrange basis. So this guy is, I would say, probably the most dominant basis used in finite elements. It's, it encompasses the classic hat functions that you know from linear finite elements. That's p equals 1 Lagrange. And for p equals 1, all the bases tend to collapse to the same set of functions. There's not a lot of ways to do this. So there is some overlap here. The Lagrange basis actually is kind of a clever way of constructing, constructing an interpolating polynomial, where essentially you construct polynomials where at a discrete set of points, let's say these 3 points, look at this, look what happens to these functions. Notice that -1, the only function that is non-zero, there's only one function that's non-zero, it's this guy, and its value is actually 1, right? And so then you come over to this point, and again, there's only one function that's non-zero, and it's this guy, and its value is 1, and so on. And so you can see the pattern here. So these functions, in some sense, they interpolate by definition. They interpolate by definition, which means if you have some function written as a linear combination of Lagrange polynomials, where you take sample points of f, let's say at some locations xi, and then you multiply it by the, I, Lagrange polynomial. Let's see. What you know is that, let's make this a little clearer. Oh, shoot, I don't want to do that. I need to redraw that again. So you have f, let's say, of x going to be equal to okay, and so what do we mean by interpolation? These polynomials give us a nice picture. Notice if I evaluate f of x, let's say I evaluate f of x at some location xj, then that's going to be f of, actually let's evaluate it at xi. Li evaluated at xi. What do you know about the ith Lagrange polynomial evaluated at position xi from this property right here? What does it equal?
1.
1. So in other words, f at xi is nothing more than, in fact, I need some better notation here. So this would be, yeah, is nothing more than f at xi, which means pictorially, so you have a function, and let's say this is f, and then you pick some points. And so then this is x1, 2, x3, x4. So this is f at x1, f at x2, f at x3, f at x4. And then you construct, let's say, some interpolating polynomial. Maybe we do the linears, right? So we just connect with a line. But notice, by definition, this interpolating polynomial, let's call this f. There we go. That's good notation. So f, call the interpolating polynomial f bar, and the exact polynomial f. So f bar, right, our interpolating polynomial, evaluated at one of the sample points xi, is by definition of the Lagrange polynomial, which is equal to 1 at xi, exactly equal to the true function f evaluated at xi. That's really what we mean by interpolation. It interpolates the true function f at the sample points by construction. That's what's nice about the Lagrange basis. It's constructed, in other words, to generate an interpolating polynomial basically by construction. And this idea here, for those of you who use finite elements a lot, this is the classical notion of what we call nodal finite elements. Is we always assume that the solution interpolates, right, the geometry at certain points, the nodes. That notion, though, is simply coming from the interpolating property of the underlying polynomial basis. There's actually nothing special about it at all. It really means nothing other than the fact that it maybe is convenient in some respects.
Well,
Okay,
also
so-
helps you frame a problem like a boundary value problem, right? Because your nodes correspond to surfaces.
Yeah, so the advantage really, I would say, is there is some simplicity in the sense that you can think of now nodes as having some true value, right? Like they're actually on the surface of either your solution or your geometry, right? So there's some value. And so in a classical like mesh generation setting, let's say this is your CAD, right? Here's my CAD and I want to mesh it. And I know that my basis is going to be some kind of a Lagrange basis. Then all I know is if I sprinkle some points on here, that I can just directly generate basically the mesh by connecting the dots between the sample points. So we call these xi's that are really just sample points. In the finite element world, they've come to be known as nodes. But it's, you see what's really cool about this is like I'm pulling back the covers and showing you where these ideas come from, like mathematically, why these ideas were picked out of like all the possible, you know, ways that you can do interpolation, and why some of them stuck to the wall and some of them didn't. So the Lagrange basis is nice is because there's this nice interpolating property. So it kind of, in some sense, makes the mesh generation process like kind of intuitive, because you know by definition of the basis that if you put the points or the nodes on your CAD surface, that you're going to get a nice interpolating polynomial, which you can then use for finite elements. And that's why we call that isoparametric finite elements. So a lot of this stuff just kind of emanates from the selection of the basis. But the important thing is that it is apt from an approximation point of view. It's just one choice. There's nothing like canonical about this choice as to why it would be superior from anything else.
Dr. Scott, I'll
Yep.
also just make a couple comments that I can think of too that might be helpful for us to talk about how these parts of our workflow might change. That what's also often a useful thing to do is to understand like displacement of a specific point on your geometry. And it's oftentimes a common practice to make sure you put a node on the point that you care about. And then all you have to do to track like its displacement is just to track the value of that node, right?
Mm-hmm.
And that's a useful property of these interpolatory bases that might be useful for us to talk about when we talk about non-interpolatory bases of
Yep.
how would I track the displacement of this part of my geometry.
Yep. Yeah, so from a practical point of view, the nice thing about traditional idea of a node in a finite element setting is that it basically gives you a discrete snapshot of the whole picture of the actual geometry of either the solution or the CAD geometry itself that you're using for simulation. But again, if you remember this idea of like Runge's phenomenon, sometimes people use Gibbs, even though Gibbs really is for sines and cosines, not polynomials, but they've become kind of interchangeable. These, if you, depending on how you pick your points, these polynomials are subject to oscillation. And that oscillation, there's no guarantee necessarily in fact, you can construct pathological examples where, like in the max norm, that oscillation really never diminishes with refinement. It just continues to oscillate. So that is an issue with using interpolation, because interpolation, in some sense, you're forcing a function to go through a set of points where energetically it may not really make the most sense for that to be the what you want to enforce.
Dr. Scott, at what point are they oscillating? Because you're starting off with, because are you totally forgetting your initial like functions or your initial geometry, and so you go back just on nodes and try to interpolate again?
Well, the way that it works is you have some object f. You say, I'm going to interpolate at these points, and depending on where you put the points, the interpolating polynomial that you compute, you know, maybe it'll be really a nice close fit, or maybe it'll be like this.
Right.
It depends on where you put the points.
And that function that we get that may oscillate, at what point is that coming in?
Well, anytime you use this basis that has this kind of what I would call a strong interpolation property, and you use it to approximate anything, whether it's in a finite element setting or any other kind of approximation setting, as soon as you pick your points and you pick this basis, you're going to be subject to this oscillatory behavior. So you could pick you can compute a displacement solution in finite elements, and depending on the function f, or the, you know, like the solution u that you're trying to compute, it may or may not be oscillatory depending on the properties of the function and the points where you've sampled.
Okay. And that's because we're not starting with a function, we're starting with like just some geometry or something, right?
Yeah, I mean, you have some function you want to approximate.
Yeah.
But step one is you just place nodes.
Right.
Right. And then
I guess what I'm wondering is why, knowing about that function initially, there's nothing that knowing about that initial function helps you to keep it close to that initial function, is because we kind of move into a new realm where it's like, now I just have points, find me a polynomial.
Yeah, I mean, it comes from the properties of the Lagrange basis and the location of the points and the properties of the function that you're trying to approximate. So we would like to find bases that don't have this property.
Yeah.
Right.
So, James, I dropped a video in the chat that might be helpful.
Okay, awesome.
Yeah, there's this has just become, you know, at this point in FEA, it's been around long enough that, you know, there's a huge segment of the practicing community of FEA analysts that you know, it's no longer even understood why or when these choices were made, and they just view it as kind of a concrete thing. And what we're doing is we're revisiting all of these assumptions at a fundamental level and saying, how can we fix them through improved spline representations? And this is one of the problems.
Yeah. Thanks.
Dr. Scott, I had a question regarding Runge's phenomenon. I remember studying this previously, and now that I've gotten into the engineering world, I guess my mind, when I think about a mesh, I just think about a linear mesh. And I'm just trying to connect those two ideas between having a linear mesh and what's going on behind the scenes, this Runge's phenomenon, how Runge's phenomenon can be difficult in finding your solution. Does it impact some of the matrices that you're trying to solve for? Or how does that come into play?
Okay, so linear, if you pick a linear, like the C0 linear finite elements, then you don't suffer from this phenomena, right? Because linears, all they can do is connect the dots. So this actually is this oscillating phenomena actually occurs in some sense mostly for the higher order versions of the Lagrange polynomials.
Oh,
So
that's
again,
right. Thank you.
yeah, so the linears are still pretty nice because there's not really much that they can do to misbehave.
Mike,
Yep.
why wouldn't partition of unity kind of wash out the error from Runge's phenomenon?
Well, you actually need one more thing. So partition of unity is half the story. Let me get to it in just, that's the next basis that we're going to talk about. So what Curtis is saying is what partition of unity means is that if you sum up the basis functions at any point, they're going to sum to 1. We call that a partition of unity. And it's actually quite powerful because it means automatically that you can represent the constants. So you already have some, here's your very first approximation result, is that if you have a basis that satisfies a partition of unity, you know that you're going to converge at least with order 1 rate of convergence because you can represent polynomials. So there you go. There, that's a partition of unity. So it's like a baseline. So it is important. Of course, it's not a very powerful approximation result because the constants aren't very rich. So, but it does give you something.
Dr. Scott.
Also, yep.
I was going to ask, does the, would having like, so these points are your nodes, correct? So would having a finer mesh make the oscillation just have a higher frequency, or does it help reduce it?
Yeah, so that's the problem with this phenomena, is that even as you refine the mesh, it can just increase the frequency of the oscillations.
Okay.
That's why it's considered to be a very parasitic behavior, is because it doesn't have this nice kind of
you can't really fix it very easily.
Yeah. Kyle, did you want to say something?
I was just going to say that partition of unity is important for representing translations. Like that's a pretty important thing to represent, and
Yep.
without it, you can't do that. So that was all I was going to say.
Yeah, a partition of unity as a baseline means you can represent constants, which are like translations, rotations, stuff like that. So it's an important property. I would say it's probably number 1 on my list for properties for a good basis. But number 2, I don't really, interpolation, I don't like interpolation personally, because it's really, you're over constraining the problem. Like you don't need to enforce this constraint. And by enforcing this constraint, you automatically engender some parasitic behavior kind of before you even begin. And so we're going to look at bases that are a little bit richer than this, or a little less constrained. Okay.
Dr. Scott, I have a question.
Yep.
So when I was reading like splines from like basic mathematics point of view, I have seen that sometimes we even use the spline basis to interpolate polynomials. So will you say that not rational splines, but just normal splines to interpolate polynomials? Will you say that even then we can see the Runge's phenomenon? So this is coming from the interpolation.
Actually, I'm going to talk about that now. So what Paloma is saying is, even if we use these other bases, which I haven't yet talked about, and then you want to sample a function, you know, the nice thing about splines is that the approximation is going to be this thing called the convex hull. And under H refinement, the convex hull converges to the curve, and the approximation has to remain inside the convex hull of of these points. So in other words, the fact that the convex hull polynomial converges means that the oscillations converge.
Okay.
Okay. But to get a convex hull, you need one other property here. So let's go down now to the basis we're going to use most, which is the Bernstein basis. And the Bernstein basis is really underlies modern CAD. You've probably heard of Bezier curves. Bezier curves are nothing more than coefficients times Bernstein basis functions. And so the properties of the Bernstein basis are very attractive and have led to really what we call CAD. Was started with the realization that the Bernstein basis was good for curve design. Okay. Bernstein bases also can be considered to be the first ingredient for almost every modern spline representation. So you've probably heard of NURBS or B-splines. They're all can be viewed as linear combinations of Bernstein basis functions as well, under certain constraints. We have things like B-splines, T-splines, hierarchical splines. They're all kind of emanate from this basic idea of the Bernstein polynomial. Okay, so the Bernstein polynomials look like this. And what you should notice right away is we don't have the interpolation property. Notice at this point here, there isn't one function that's one, right? There's all three functions are non-zero. So there is no strong interpolation property here in this basis. But what you'll notice is we have a couple of important properties, and these are the big guys. I already talked about partition of unity. And then on top of that, we have something called positivity. Notice all these functions are positive. Positivity actually is really, really a nice property to have. And it will lead to a lot of the nice behavior of Bezier curves. So if you were to represent a function in terms of the Bernstein basis, let's say you wanted to represent some curve, what you would do is you would generate you would pick the coefficients. Let's say these are the coefficients. So this is x1, x2, x3, x4, and let's call this a curve, C of xc. So a Bezier curve, C of xc, is nothing more than a linear combination of the xi times the Bernstein polynomials. But notice how the nodes, these are what we were calling nodes before. Notice the nodes now in the CAD world are called control points. They no longer interpolate the curve. It's non-interpolatory because notice you don't have this Kronecker delta or strong interpolation property because all three functions are non-zero. So you can kind of think of a Bezier curve as essentially tracing out the weighted average of the nodes. And what's really cool about Bezier curves is as you add more and more Bernstein polynomials, the curve doesn't change, but the control mesh oh my. Be careful with find the control mesh. this, we call this a control mesh sometimes, but it's nothing more than the location of the coefficients. As you refine, the control mesh gets closer and closer to the curve. And that's coming from this non-negativity and partition of unity property. We call that the convex hull property, which means you essentially snap a rubber band around the points, and the curve always has to be inside of the polygon created by those rubber bands. That's the convex hull. And so as you refine, as you add more points, the convex hull converges to the curve, and you don't have this oscillation. It's not possible because of these two properties here, non-negativity and partition of unity. And that's what makes it nice for design, because designers grab these little nodal locations and they move them around, right? And as they move these points around, the curve naturally follows the shape of this control polygon. And that's what gave rise to its popularity in design on a computer, is because of this really nice relationship between the locations of the nodes and the location of the curve. And also, what we're going to learn from an approximation point of view is very powerful as well. But you should realize that mathematically, these are the two ingredients that matter, is non-negativity and partition of unity. That's why we get this picture. Okay, so I'd like you to I want to move on to now finite elements in the next lecture. I'd like you to go through these examples in detail so that you can see. I actually did an example of Lagrange interpolation from a Galerkin point of view here, which should be instructive. And then we did Galerkin approximation with both the Bernstein and Legendre bases. And what you should see immediately is the mass matrix for the orthogonal polynomials diagonalizes. That's why they're nice, is because it diagonalizes the operator and it makes it easy to invert the mass because it's just a diagonal matrix. Whereas with the Bernsteins, you get a full matrix. And then we do some solutions, some approximations. Okay, so I'll let you study that on your own. And next time we're actually going to dive into, we're going to do an axial bar, strain energy. We're going to do real finite elements with splines and all that kind of stuff. Okay, so let's stop there. I'll hang around for a few minutes if there's any kind of questions remaining, lingering questions. But thanks everybody else. Appreciate it.
Dr. Scott, I had another question on the Bernstein polynomials. So I was wondering if they also, like if you were using equally spaced points and you were increasing the polynomial degree, if they also suffer from the Runge phenomenon, or was that convex hull property that you were talking about, was that saying, hey, it does not suffer from that?
Yeah, so if you have a function, so you want to approximate a function f, and you want to construct a Bezier curve that passes through a certain number of points, then what you're going to do is you're going to solve for the nodes so that the curve C interpolates. And so maybe that gives you a Bezier curve that looks, I don't know, maybe something like this initially. I don't know, something like that. That curve has a control polygon that maybe, I don't know, maybe looks, this is not exact or anything, but maybe the control polygon looks something like that. And so what you know is as you refine the control polygon, because of positivity or non-negativity in the partition of unity, this curve has to stay inside the convex hull of this control polygon. And this control polygon is converging to the exact curve. And so that gives a nice it doesn't eliminate oscillations entirely, but it's less oscillatory. Of course, this control polygon is converging at a very leisurely pace. So it's not like converging really fast, but you do have nice control over the curve. It has to stay inside that control polygon.
Okay, so you still suffer a little bit from that, but not as extreme as is what you're saying for. Okay.
Yeah. Yep.
Thanks.
So Dr. Scott, will you say that this is just like simply mathematically Bernstein basis helps us to take like just a convex combination of the control points and therefore we are always stable?
Yeah, that's the basic idea. It's like a weighted average. That's what positivity gives you. It's like you can assign mass to each of the control points, and those masses are always positive. So it's like really like taking the center of gravity of the control points. That's what's traced. That's what the curve is. Okay, any other questions?
Dr. Scott, I had a question real quick about the updates you made to the homework. So with the way we're going to do homework now, do you still want us to submit our work that we've done and then just later on submit the score that we give ourselves, or do you just want us to submit the score now?
Yeah, I would say you can submit. I'll go through and enable that. I don't think it's currently enabled because I just made this decision this week. I don't know if you heard, but in Utah County, they just went to an orange level, which I know like my kids' schools have all just announced today that they're not going to be on campus as much. And I'm assuming that BYU and UVU will probably follow suit. So I just decided this morning that I'm just going to let you guys kind of self-moderate. So later today, I'll go in there and enable an effort score that you can give yourselves, and I'll put some directions on how that works. And so you can go in and do that. And part of the effort score is going to be the assumption that you go back and correct your homework, right? So, but it's really on your honor, I guess.
Okay, thanks.
That takes some of the stress off.
Yeah, it does take quite a bit of the stress off.
Okay, good.
Mike, can I ask you a question?
Sure.
So we talk a lot about how certain basis functions represent certain solution spaces well. And one of the premises of IGA is that we can use a given basis function to represent a geometry and a solution space. And my question is a spline that represents a geometry well necessarily the best basis function for representing the solution of your boundary value problem?
Usually it's not. Usually the representation of geometry is in the context of a basis that's very coarse. So you can represent geometry with very few basis functions. And usually for a solution, you're going to need orders of magnitude more basis functions. But what's nice about splines is that you can enrich the space or refine the space and preserve the parametrization of the coarse scale geometry exactly. In FEA, right, because you're interpolating with these Lagrange interpolants, every single time you change the nodes, you change the interpolant or the parametrization. Splines aren't like that. They have because of this non-negativity and partition of unity, when you refine them, you preserve that parametrization exactly. So the coarse scale geometry always lives in your finite element solution space. That's the big difference. I don't know if that was helpful or not, Curtis.
Hey, so I have a question about that. So you mentioned this earlier, that with the Bernstein shape basis, you can increase the order and not change the interpolation. So you could change it depending on, I mean, you're adding more degrees of freedom. So you could have it represent something higher order, but I think what you're saying is you can add those additional points, but you're still preserving the lower order representation. Is that, am I understanding that right?
Yeah, if you wanted to change it, you could. Normally when you do like H refinement, if you can fix the parameterization of the geometry, then, you know, if your parameterization changes with every refinement, it will actually destroy your convergence rates. So if you can fix the quote unquote geometry that maybe is represented with 100, you know, 100 elements, and then you refine that space exactly so that you create larger and larger spaces, and the geometry space lives in every one of those bigger and bigger spaces as you H refine, then you can have 10 million nodes for your solution, and the geometry, the actual parameterization of that geometric object, will live in that space. And so it's fixed and it doesn't disrupt the convergence behavior of the method.
Okay, thanks.
Can I repose my question in a slightly different way, Mike?
Sure.
I think I'm feeling a little more abstract than I think I'm conveying. So suppose we're looking at a 1D problem that's a wire. That's my favorite way to think of the wave equation. And so you bend it with some load that gives it a parabolic shape. Your optimum solution, like your optimum basis for that, would be a second order polynomials.
Mm-hmm.
But that it would not necessarily be the best basis for representing the geometry of a line.
Yeah, that's a fun example. Let's say that we've got, here's our little beam, and let's say we represent it with a line. So the Bernstein polynomials look like this. That's the base, that's all we need for geometry, right? Let's call that space 0. So the space spanned by these functions generates space 0. What you can do is you can enrich this basis and transform it, let's say maybe into add a bunch of nodes, increase the degree, maybe you create like a spline basis that looks like this, whatever, right? Something like this. Let's call this S1. The key is that S0 lives in S1. So this geometry, you can still represent it exactly inside of here. So as you refine, you're not perturbing the geometry every time, or the parameterization of the geometry. So that's the basic idea. Whereas with like Lagrange finite elements, maybe you can do it, the line's like a little bit trivial, but if it was curvy, you wouldn't necessarily have that property. And so you generate basically non-nested spaces. And so that engenders errors.
So then you're saying in every case, you can show mathematically that the space that can represent your geometry has a subspace that would be your optimum solution space. Maybe
if what you said was a restatement of this mathematical statement right here, then I agree.
I don't know if that's what I said.
Right? So it just means every function in S0 can be represented, and it lives inside of S1 too, including the geometry. The geometry is just a function that lives inside of S0. And so what I'm saying is under refinement, spline refinement, the function that represents geometry, since it lives in S0 and S0 lives in S1, and then of course, I mean, like it just goes on and on, right? To Sn, then geometry also lives in here.
So the only way that what I said would not be true would be if the solution space required, the optimum solution space was above the geometry space, which seems unlikely in most cases.
Yeah, it's only if, I mean, if the optimum solution, if you needed to construct a space, for example, that had like sines and cosines or something, it wasn't even polynomials, then of course, right, there's no relationship, right? Like everything is still a polynomial here. So maybe, you know, you're like saying, well, maybe my optimal solution space is a bunch of exponentials and sines and cosines or other analytic functions. Then there's, you know, well, there are actually still ways to do this. We'll talk about it. You can still preserve the geometry, but anyway, we'll talk about that next time, Curtis. You're getting ahead of yourself here.
Okay, thank you. I think you've answered my question.
Okay, anything else? Okay, well, great. Well, thanks, everybody.
Hey, hold on, Mike. Can I ask you a different question?
Sure.
So I asked you earlier if partition of unity doesn't handle the error from the oscillations that you would get from P using P Lagrangian P elements.
Here's the thing. I like last week, I spent some time trying to find a conclusive result about, and are any of my students still on? Maybe they know the answer to this.
I'm still here.
I was not able to find a conclusive result that said, if you move to bases that have a partition of unity and positivity, that somehow that implies an improved oscillatory behavior. I think that there are a lot of kind of examples where you can see this, but I'm not aware of any like mathematical result that says that. In fact, I'm fairly certain I could generate even with splines for a given, like if you wanted to approximate the step function with smooth splines, you're going to get oscillations, right? Even with smooth splines.
Yeah.
But what you see in practice is that it's not nearly as bad if the splines are really smooth and higher order. But I actually tried to find something that like stated this conclusively, and I couldn't find anything. I still think that, I mean, I think every polynomial basis suffers from some of this undershoots and overshoots, period, right? No matter what, it's just how bad it is.
I would say that having those two properties does allow, like, from a designer point of view, more control over those oscillations, in that you have that convex hull and you can kind of bound things better.
Yeah.
So Kyle, when you go back to a solution space though for FEA, and your basis is just interpolation for your solution, and your patch, you're doing P elements, these Lagrangian P elements that are only evaluated in between on your element, right? They don't have a broader patch. So they'll satisfy partition of unity. So when you sample your solution space, you'll still convert. It's not like you're going to get a negative stress or something, right? Because they do evaluate to 1.
I guess I don't quite understand the comment about negative stress.
I'm trying to understand. So I know that I understand what you wrote about how the P elements have, these fundamental differences that end up manifesting in spectral properties, and that makes sense to me. But now I'm thinking about it in terms of just mapping a solution space. Like, why would a negative oscillation be a problem when you have another function right there making up the difference? That's what I can't quite wrap my head around that.
I don't think we understand your question, Curtis. So maybe you'll write it down or something. I don't know what I can say.
Can you say that again, Curtis?
So when you do like I can't scroll, it's my screen. When you have P refinement and you end up with, like, suppose you have a solution space where there is negative interpolation, but you maintain partition of unity by having multiple functions there. How your solution space would still evaluate to the correct solution. Like, for instance, you would not get a negative stress just because one of your shape functions goes negative.
Oh, you can. Like in the mass matrix with Lagrange, you can have, this is one of the problems that you can run into with basis functions that are not positive, is you can get negative mass.
How is that possible if you have partition
Mike,
of unity?
can you open up the chat and just pop open the video, the link that I sent?
Sure.
So I made a video earlier this year as I was taking the 602 class or whatever the class after this one is. But so this is just a quartic Lagrange, and just if we just move like this one middle node, so what you can see is that even by moving this middle node out, like on parts of the element, you're actually compressing it, right? And so even though you would have expected,
this is great, Greg. I need to add this to the course notes because that's perfect.
Sure. So like this is the idea, right? If you move that one little node with the Bernstein basis, it's not interpolatory. If I move it all in, everything's in compression. If I move it out, everything's in tension. And this is just like with larger deformation. This is the Runge phenomenon that you actually can invert. But just like this idea, that's what ends up happening, is that that's where you can get your negative stresses or even the inversion from. That you don't get that with these interpolatory bases. That in this case, again, everything now is in tension, everything's in compression. Back to tension and back to compression. So that's, after this, it's just kind of a wonky explanation, but for video, that's like a circle. But anyways, that I guess is answers the question that you were having, Curtis, to some extent, of how you get those negative stresses.
Yeah, Greg, that's a perfect answer. Thank you, because I see it. It's more of a global thing. It's not
right.
Thinking about it too
right.
local.
Because if you go back to the quartic Lagrange on the square, so you can start to see. We saw kind of like this exact same shape of this Lagrange, but if you go back to the video, though, Mike, is what I meant to say. If you just go back to the beginning, that right, the way you can think of it, and if you pause it as soon as it, like pause it now, when it's at max deformation.
Okay.
So it's like you have a quartic polynomial that has to interpolate those 5 points. And so it can't be a straight line on like from the bottom left node to the next node. It can't be a straight line and then shoot up. And so it has to overshoot to come back to be able to interpolate that point on the corner. And that's what you start, and you'll even see that if you go to the second of the Lagrange videos with like the ones that you'll even see at like the top of the element, you'll see the oscillations even up there. That you don't see the oscillations in the Bernstein examples, which they'll be more obvious on the large deformation ones.
Yeah, so Curtis, visually this is nice. You can actually see the robustness, right?
Yeah. No.
Look at the top of this element, and you see like even the oscillations occur up there.
They're moving, yeah.
And that's to maintain, because it has to interpolate, right? In this case, this tensor product basis function has to interpolate all of those nodes. And so globally, it's happened to modify. Anyways, so hopefully that's a helpful.
Yeah, let's add these links to to the, I'll get with you. Actually, can you just stay on the line?
Yeah, I can do that.
Yeah, this is good, Greg. Thank you. It's like really deep in FEA theory to get to this point, but this is exactly answers my question.
And this is why we don't use, even like in commercial P element methods, it's one of the reasons why they don't use Lagrange once you go above like quadratics. I think most PFEM codes commercially switch to Legendre.
Most PFEM, I can only think of two. How many are there? There's stress check, one
yeah, well, so like even Tyler Stone, and so James, we're gonna have to probably cut this out. You know, Tyler from our group, he had written for his, when he was a grad student, he was writing a PFEM code using Legendre, right?
Mm-hmm.
Anyways.
Yeah, that's true.
Anyways, but so you just don't see that. You don't even see like Lagrange, like fourth order Lagrange with like optimal, point locations. I don't know if they're like the Lobato points or whatever they are. You don't even see that. You see them all switch to Legendre above quadratics. So.
Okay, good. That was great. Thank you, Greg, for pulling that out. Let's add that to the notes. That's a really nice visual.